Uh, Good morning again. Now we are into module 4 after finishing the second part of module 3, that is Fourier series. Okay, see here this Fourier series we have completed. Fine. Fourier series is for continuous time periodic signals, and for discrete time it is discrete time Fourier series. It is for discrete time periodic signal. It's discrete time Fourier series, which is not there in the syllabus. So that's why we have not dealt the discrete time Fourier series. We just have dealt with Fourier series, which means that to particular it is continuous time Fourier series. Understand? Now we are switching to fourth module now. Fine. In fourth module, you will have the DTFT as well as FT. DTFT means it is discrete time Fourier transform. This is Fourier transform. Here, as the name suggests, it is discrete time, discrete in time, and it is discrete in time as well as the non-periodic. If it is periodic, it is Fourier series. If it is non-periodic, it is Fourier transform. And if it is non-periodic continuous time, it is continuous time Fourier transform or just Fourier transform. And to be particular, if it is discrete time, we have to attach this terminology discrete time Fourier transform. So the first thing that we are seeing in module 4 is for discrete time Fourier transform. Okay, after this, in the same module, we'll be having Fourier transform, that is continuous time Fourier transform. Continuous time can be left out. If it is left, okay, it by default means that it is continuous time for Fourier transform. And then here also by default, if the continuous time is missing, it means that it is continuous time Fourier series only. Similarly, these two are for continuous time, as it says. Again, these two for discrete time, and these two for periodic signals, and these two, that is the Fourier transform and discrete Fourier transforms, are for non-periodic. Okay, and now since we are dealing with the discrete time Fourier transform, okay, we have to understand the discrete time signals. Okay, where had we seen the discrete time signals earlier? In which transforms? As I've told you earlier, not all the transforms are suitable for all types of signals. Laplace transforms are suitable for continuous time signals, no matter periodic or non-periodic. Okay, Z transforms are applicable for discrete time signals. Okay, discrete time periodic as well as non-periodic. But if you come to Fourier transform, it is for discrete time as well as continuous time, but for non-periodic. Okay, that's why we are considering the discrete time signals, but these discrete time signals are non-periodic signals. Fine. Now let's get into this. Yeah, discrete time Fourier transform. Okay, the DTFT, it is in short called as DTFT. It is applicable for discrete time signals which are non-periodic in nature. Understand that? Now, since we are dealing with discrete time signals, okay, and since the Z transform was also dealing with discrete time signals, let's see how these two transforms can be compared. Okay, if you're really good with Z transform, this DTFT is not going to pose problems to you. You can easily understand DTFT. Okay, so for that you need to be good with Z transform. I hope you all are preparing for Z transforms because the test is approaching the first internals. Okay, so for that you're all preparing for Z transform, right? Z transform and the first module. Okay, so how this Z transform is connected to this DTFT? Let's see that. See, this is how the Z transform equation is given. Okay, if there is a signal, discrete time signal x of n, okay, then in Z domain it looks like x of z. And how to obtain the Z transform of x of n? By applying this equation. Using this equation, we can obtain the Z transform of the discrete time signal x of n. Yes, when we said discrete time signal x of n, we were not bothered whether this x of n is periodic or non-periodic. This being discrete is sufficient for application of Z transform. So this is something that we have seen. Now, in this Z, wherever you're seeing Z, if that Z is replaced by e power j omega exponential, this complex exponential, if you replace this Z by, then it becomes DTFT. Everybody understand that? It's quite simple. You need to understand this way. Okay, we know the equation for Z transform, that is x of Z, which is applicable, which is applied on signal x of n. Okay, DTFT is also applied on signal x of n only. But how DTFT, the equation for DTFT looks like? The equation for DTFT looks like, okay, this. What we have done, in place of Z, we have brought e power j omega. Understand that? In place of Z, we have brought e power j omega. See, in this place n, there is Z right here. So Z is replaced by e power j omega. So it's e power j omega to the power minus n. This is e power j omega to the power minus n. So this minus n is always there. This minus n is there. But Z is what? Z is e power j omega. I hope you have understood this. So how we are obtaining the equation for DTFT? We are obtaining the equation for DTFT by replacing Z by e power j omega in the equation for Z transform. This is how they are related. The Z transform and DTFT are related. Understand? You replace Z by e power j omega, you have DTFT of the signal. Understand that? So this is how one should remember, and this will make your things simple. Now, the discrete time Fourier transform or DTFT of a non-periodic signal x of n is given by that equation. That's something that we have just seen. Okay. In this, x of n is what? This x of n is non-periodic discrete time signal. Fine. Okay. And that is given by this. Fine. Since this is non-periodic, we are taking an integral here. 1 by 2 pi times minus pi to pi x power e power j omega, x of e power j omega into e power j omega and d omega. So here we are integrating this with respect to omega. And why we are using this omega? We are dealing with the discrete time signal. Understand? Now this equation is important for us. What is this equation? This is the equation which transforms the discrete time signal x of n into time domain signal x of e power j omega, where x of n is represented like this. Understand? X of n is some discrete time non-periodic signal. Okay, and if you have to take this discrete time non-periodic signal into frequency domain, then we use this equation, and this equation is called as DTFT. Okay, and these two equations, okay, are called the x of e power j omega and x of n. They are called as DTFT pair. Understand? As we have been seeing, even in Fourier series, we saw in Z transforms, we have seen in Laplace transforms, we have seen when we studied that in last sem. Okay, every transform have got transform pairs. Why do we call it so? Why do we call them as transform pair? Because there cannot be one signal without the other. That's why they are pair. They are always existing. That means if x of n is there, there should be the frequency domain signal x of e power j omega, and if x of e power j omega is there, okay, there should be some way out to take that x of e power j omega into time domain, that is x of n. Understand? That's why they are referred to as the transform pairs, the DTFT pair. Okay, and they are represented like this. Okay, and what is this equation called? This is x of e power j omega. Why do we have to take x of n into frequency domain? This is time domain signal. This is frequency domain signal. Why do we need to operate in frequency domain? Because in time domain, we don't have the frequency information. I've told you that I've taken enough of time for that when I was explaining you the Fourier series and the introduction to the transforms in general. Why do we need that? Because in time domain, we can differentiate the sound of different persons, the voice of different persons, because their voice contain the different frequency components. But which frequency components are differing? Which is the dominating frequency in person A, which is the dominating frequency in person B, and that is what is going to decide how the voice is going to sound like. Okay, and there we can differentiate between the voices of two different people because they have got different dominating frequencies. We know they are different, but what are they? Which frequency is different and which is the dominating? So if you have to extract that information, we have to get into the frequency domain. So this in frequency domain, it is called as analysis equation. In time domain, it is called as synthesis equation. So that means if you give me the frequency components, I'll build x of n. Okay, and I know how to get x of n into frequency domain. That is by using this formula. Everybody understand? So this is analysis equation where I analyze the frequency information being in frequency domain. Okay, and then we come into x of n, come into time domain, that is x of n. So to go from x of n to x of e power omega, you have to apply DTFT, and to come into time domain, you have to apply inverse DTFT. Understand that point? So x of n is in time domain, x e power j omega is in frequency domain. And what is this frequency domain signal can also be referred to as this can be referred to as what? That frequency domain, even in Fourier series was, we saw that the frequency domain signal was being referred to as the Fourier series coefficients, or in other words, it is spectrum. Okay, similarly, x e power j omega is the coefficients of the signal x of n, the DTFT coefficient, mind you. It is Fourier series coefficient we used to differentiate by attaching the term Fourier series. We have to attach the term DTFT coefficients. Okay, so this is DTFT coefficients of x of n in frequency domain. Omega here refers to the frequency, the angular frequency. Understand that? Okay, so that is what is being said. This is in time domain, this is in frequency domain. Now x of j omega is also called as spectrum of x of n, because in x of n all the frequencies are combined, wherein in x e power j omega we are separating the frequency components so that we can see them properly, we can understand them properly. Okay, now let's see how this e power j omega behaves if we add this 2 pi k or 2k pi to this frequency. Understand how it is going to behave? Fine. The spectrum, how it is going to behave if we do this operation on it, is what we are trying to look at. Fine. See here, this is the equation. In this equation, in the equation for x of e power j omega, in this equation, okay, there is another frequency component added to this. That means there is being a shift in the frequency. Fine here. There is a shift in the frequency. The same shift you bring here also in this exponential. Fine. Now there are two exponentials in it. One exponential is e power minus j omega n. Another exponential is e power minus j 2k pi n. And this exponential becomes 1. And when this becomes 1, what is this? This is e power. This is x of e power j omega. That means if you add 2k pi to this, it is not going to change. We are going to get the same signal back. What's happening here? What's happening? What is happening here is what is the what Implication of this, if we add this to the frequency, we're getting the same signal back, same frequency spectrum back. What is this indication? It indicates that x of e power j omega is periodic with fundamental period 2 pi. There is a k here. This k is a constant. You just give any integer to this. Okay, you should get the same signal back by adding 2 pi to this omega. So 2 pi is the fundamental period. Suppose you have some frequency domain signal. Okay, into that frequency domain signal, you add 2 pi. That means again you are getting the same signal back. That means after every 2 pi radians per second, okay, what's going to happen if after every 2 pi radians per second, the same spectrum is repeating. So that's why this spectrum here is periodic. Okay, let me go back to the table that I had shown here. Here, the Fourier series is applicable for continuous time periodic signal. We saw the signal that we need to consider is periodic. But in frequency domain, the spectrum for Fourier series is non-periodic. The signal here is periodic, but the spectrum is non-periodic. Understand? Here, the signal is non-periodic, but the spectrum, the frequency domain signal is periodic. Understand the difference between the spectrum of Fourier series and the spectrum of DTFT? Okay, spectrum of Fourier series is non-periodic. Okay, spectrum of DTFT is periodic. Another difference is Fourier series is applicable to periodic continuous time signals, whereas discrete time Fourier transform is applicable to non-periodic discrete time signals, as it very clearly says. So maybe we can just extend some more information here. Okay, Fourier series is for continuous time periodic signal, but the spectrum is non-periodic. Here this DTFT is for discrete time non-periodic signals, but the spectrum is periodic with fundamental period 2 pi. Understand? So that is what is proved here by this. So what can be asked in the exam? They may ask, is the spectrum of DTFT periodic in nature? If so, what is the fundamental period? Okay, so what we are doing here is, instead of dealing with the time domain signal, we are dealing with the frequency domain signal. So there we were in time domain. What is the test for periodicity? It is adding t plus t naught. See, x of t plus t naught should be x of t, right? So then we were adding the time, adding the fundamental period to the time. Here we are adding the fundamental period to the frequency. Understand? This is in frequency domain. Just that the test for periodicity remains the same. Okay. So after adding 2 pi k, since we are getting the same signal back, so k is an integer. You just bring any integer to k. 2 pi into 1, 2 pi into 2, 2 pi into 3. Anything you do, it will give me back the same spectrum. That's why we say this spectrum here is periodic with fundamental period 2 pi. Understand that? Okay. So now, since x of e power j omega is periodic, what is true? It is infinite. We have discussed this many a times when we were learning the signals in first chapter. What is that? When can we say a periodic signal? When can we say a signal is periodic? Very first thing that we should look at is its length. It should be infinite in length. Okay. Then after being infinite, that is one of the conditions. One of the conditions is it should be infinite in length, but that is not sufficient condition. One of the conditions is, but it is just being infinite length is not periodic. So after being of infinite length, the signal should be repetitive in nature. Okay, so a repetitive signal which is infinite in length can only be periodic signal. That's why, since the spectrum is periodic, it should also be an infinite series. Okay. Now, another thing that you should understand, this spectrum will exist only if x of n is absolutely summable. What is absolutely summable? X of n is a discrete time non-periodic signal because we are applying DTFT. That is understood. What is being absolutely summable? Absolutely summable. What does that mean? This is the meaning of absolutely summable. That means you consider x of n. Okay. And you add all the components of or all the samples of x of n. Okay. Let the length be anything. Let the length be anything. Okay, take it from minus infinity to plus infinity so that we'll not be missing out on any of the samples. So add all the samples that is there in x of n, and if you do that, that should give you a number less than infinity. That means it should be a finite entity. The summing up of all the samples should give you a finite number. That is what is called as absolutely summable. That means after summing up all the samples of the signal x of n, we should get a finite number. It should be a number which is less than infinity. Then it is called as absolutely summable. So if this condition is true, then only this exists. Then only this exists. So what type of signal is x of n? What type of signal is x of n? If we say it's absolutely summable signal, we have another terminology for that. We have another terminology for that. What is it? It should be a converging signal. Converging signal means what? The value of the signal should be approaching to zero. Approaching to zero. If it is not getting zero, then also it's fine. But it should be approaching to zero. That they are called as converging signals. They are all finite signals, bounded signals. So there are so many terminologies which are more or less the same. Okay, so in this case, x of n, if we say it's absolutely summable, we can also say x of n is converging. Okay, when we say it's converging, we can say that its amplitude is bounded. It will not go to infinity. Its amplitude is not infinite, so it is bounded signal. Understand that? So if it is converging or absolutely summable or a bounded signal, then only I can apply DTFT. Then only this spectrum is available. Otherwise, no. Understand that? It should be bounded means it should also be of C. If suppose x of n is 1, if you add them up, what will happen? It will become infinity. No, x of n should not even be that type of signal. It should be bounded finite length signal. In that case, x of n can be finite length, but x of e power j omega cannot be finite because it is periodic in nature. So you should not mistake between the time domain signal and frequency domain signal. Get that point? Now let's look into the properties of DTFT. Okay, so before going to the properties, let's understand what is DTFT. DTFT is discrete time Fourier transform that is applicable to x of n. What is x of n? X of n is discrete time non-periodic signal. Okay, so if you apply DTFT on discrete time non-periodic signal x of n, then we get into the frequency domain. Okay, where we obtain the spectrum x e power j omega, and x e power j omega is periodic in nature. Okay, and x e power j omega, the spectrum, would exist only if x of n is absolutely summable. That is what we've seen. Fine. Now let's go on with the properties. The properties again are the same, something that we have seen for Fourier series, something that we have seen for Z transform. The same set of properties would repeat. Okay, so you should not be having any problems understanding the properties here. Fine. So let's see the first property. Okay, so as we have seen for all the transforms, here also this transform also is linear in nature. That means to check the linearity, we need to have two signals. Okay, and the two signals are not just the signals, but they are weighted signals, and the input that we consider is weighted sum of the signals x of n and y of n. So this is also called as the linear combination of signals x of n, y of n. I had not given you that term. So this is called as the linear combination of x of n, y of n. Understand that? So this is linear combination. So always, if you have to go for linearity, okay, then the input should be the linear combination of the signals. It need not be linear combination of just two signals. Instead of taking two signals, we can take three signals, four signals, more than two signals you can take. Understand that? More than two signals you take. But for explanation sake, we take just two signals. So we are considering the linear combination of the signals instead of consider the signals alone. Understand that? So if you apply DTFT on this, what happens? We can always separate this A from the signal, and you can apply the DTFT on the signals, which would look like this. This is what linearity is. So all the transforms are linear in nature, means we can always separate the scalars associated with the signal and apply the transforms only on the signal. That is what is important here. Okay. Now let's look into the proof. So x of e power j omega is given by this, y of e power. Why do we need these two in frequency domain? Because we have those two as time domain signal. X of n is a time domain signal, y of n is another time domain signal. Understand that? Now, so you should to obtain x e power j omega and y e power j omega, we have to apply Fourier transform. So we have applied the Fourier transform on x of DTFT. We should be saying we have applied the discrete time Fourier transform. Let me say DTFT. So we have applied DTFT on x of n and y of n. So we have obtained x e power j omega and y e power j omega. Now, so if we know these two are the spectrum of the input signal, then the z e power. What is z? Why we are seeing this? See, z power n is the linear combination of the input signal. So what is z of n? Is this? Okay. So in place of z of n, you bring the linear combination of the signals. That is the sum of the weighted signals. Okay, and apply this summation along with this exponential to both the terms. Okay, keeping the scalars out of the summation because it has got nothing to do with the summation, because in summation n is running from minus infinity plus infinity, so only the function of n have got something to do within this summation, so scalars are kept out. Fine. So if you look at this term and this term, you will understand they are the spectrums of x of n and y of n. So this is what linearity, quite a simple stuff, and you all understand that. Fine. Now, what is the next property we have? Time shift property. So this is shift in time. Yeah, the shift in time. If x of n is there, the DTFT application of DTFT will give us x of e power j omega. Now, if the same signal x of n, if it is shifted in time, say we are right shifting it, minus n naught is there. Okay, in Z transform, what used to happen? You used to have z to the power minus n naught, right, along with x of z. Along with x of z, you used to have z to the power minus n naught because you have minus n naught here. So what is z? Z is e power j omega. So always remember z is e power j omega. If you just get that memory of something that you've learned in Z transform, then the things will fall in place very easily. Okay, so you do not have to bother much and memorize these things. Okay, and there's nothing that you're learning afresh, learning something new. No, if you know, if you've understood Z transform and if you know what's happening with the properties, okay, so the same thing would come here for the frequency domain also, that is using the DTFT. Fine. So in place of z, we have e power j omega. So since it is z to the power minus n naught for x of n minus n naught, so z replaced by e power j omega. So it becomes e power j omega n naught. E power minus j omega n naught because there is minus one. If this is plus n naught, it is e power plus j omega n naught x of e power j omega. Understand this point now? So we need to consider the equation for the spectrum, that is x e power j omega. This is the spectrum equation, the analysis equation. Okay, the equation in frequency domain, the equation for frequency domain. So this is consider the DTFT. Okay, now in this place of x of n, substitute x of n minus n naught. That is what is done here. So they have taken this as y of n, right? So that's why they are going for one more. If x of e power j omega is this, y of e power j omega is supposed to be this. Is what they have written. Okay, I'm just following the textbook. This is taken from Uday Kumar. I'm just following him. Find nothing new. Okay. Now, now in place of y of n, you bring x of n minus n. You could have avoided this having y of e power j omega. You could have avoided if you had avoided this y of n here. Okay, you could have just left this y of n and you could have brought x of n minus n not directly in this place. But let it be, not a problem. You're just writing the equation and you will practice also by writing it twice. So let's see it positively. Just substitute that x of n minus n naught. See, y of n is the shifted x of n. So bring that shifted x of n minus n naught in place of y of n. Understand that? Now, how to deal with this? Now, this is not in the standard form of any transform. There is n minus n naught, right? So we can play with that n minus n naught. So let's have a substitution m in place of n minus n naught. So that means in place of n minus n naught, you substitute m. If you substitute this as m, what would your n be? What would your n be? Your n would be m plus n naught. Yeah, so n would be m plus n naught, and n minus n naught, which was here, is replaced by m. Okay, simple stuff. Now again, you found the two exponentials here. Fine. So bring two exponentials and bring this exponential, which is the function of n naught out, because here we have m, right? Soon after this becomes m, you have to change this integral, sorry, this summation variable also to m. Whatever is here should come here. Okay, so m is running now. Since m is running, this exponential has got nothing to do within the summation, so keep it out. Okay, and this is what it looks like. This is x e power j omega. Everybody understand this? Okay, so this is regarding the time shift property. Fine. So in the next class, we will see some more properties. So we shall end it here today. Fine. So I want you all to give your attendance now before the end of this session. Go on, everybody.